Participants in the science fair once again this year on March 3rd at the Louisville Science Center. You must turn in the paperwork online. So I'm going to show you that again. Here's the paperwork, stapled. You have to fill this out and turn it in online by the 21st. Now, if you don't have the paperwork turned in, you don't get to compete. And that's a way that you eliminate other people, right? Because they just couldn't get the paperwork turned in. They might have had a great idea, but too bad because you didn't turn the paperwork in. You got the no-go. So in life, you can do a lot of great things just because some people just can't do paperwork. Remember that. So right here, you can see that we have water, oxygen and hydrogen, just like you see over here. And Cody did this correctly because you can see that he has initially one oxygen and two oxygens here. That's the problem. So he puts a 2 here. That gives us 4 hydrogens now. That's why he needs a 2 over here. Now the 2 tells you have 2 of them. So if you want to see it like this, that's what this 2 is telling you. You have 2 of them.
Is that not a,
yeah.
Next to O2, you put a number.
There'd be 1 there. So if you saw it on a test, it'd be like 2, 1, 2 would be the answer. Right. That's how they'll test you. So it's important to know that that is a 1.
Okay.
Yeah. So there's 2 here. Good question. Sheet version 5, Cody. We got the single displacement reactions, or this one is examining the synthesis reaction. So they have them kind of in a different order here. This up here is a combination or synthesis. Now, how do you know that it is a combination or synthesis reaction? What are you looking for? No, just 2 elements. Like this first one up here is a synthesis. You're making water. See, everybody see you're just making one thing? This is like the basic of the basic. You got the elements, you make a compound. So synthesis reactions always have some elements and you're making a compound. Synthesis or combination reactions. Decomposition is the opposite of synthesis. So you can see here how you have a substance like a mixture, and it's decomposing into 2 different elements. Once again, you still have to balance this. Initially you had 1 Hg, you had 2 O's, diatomic. So you have to balance that with the coefficient there. Over the homework, doing a couple homework problems. So we can see here that the Na was not balanced and we just balanced them. Anybody come up here and finish this for us?
She fell asleep on the plane and she woke up with an Irish accent. She's American, and she spoke it like full, like properly. But there was like no flaws in the way she spoke. Well, yeah, but usually when like in Dublin they don't have like they have the words like us, but they have an accent. Oh. But like in some parts of Ireland.
Okay, nice shot. Now look right here, you got 2 oxygens there, now you got 4 here. You're on the right track.
Wait, okay, so there's 2 oxygens right there. So if we have 2 oxygen. So that way we have 2 of these and 1 of these.
Now draw the line and add them up. Put your coefficients here.
Oh, so just 2, 1.
How come you got over there?
Oh.
Nope, there's 2. See them? 1, 2. Make sense?
Oh yeah, I got it.
In a compound of a less active metal, Fe solid plus C copper NO3 to.
Rain did a nice job reading about single replacement reactions. In these type of reactions, you always have an element and a compound, and they're going to replace. So you end up forming new products like potassium hydroxide and hydrogen. Now this looks very similar to decomposition, where you're actually correction a double replacement where you're getting two things. But remember that this is aqueous, this is a gas. A single replacement typically involve an element and a compound. That's how you know that it's single replacement, because this is an element here. So if you're checking, you always look at your reactants. Is everybody clear? Whenever you determine a single replacement reaction, it's always going to be one element and then a compound reacting together. These would be notes. If you drop a piece of zinc into a solution of copper nitrate, we've done this reaction in the lab, you'll see that copper forms. Now here's your element, here's your compound. You can see they switch. Now the question is, Nate, why do they switch? Now chemistry is a lot like life, right? This happens quite frequently. You know, you have a metal that's not very strong, and then a metal that's stronger comes along, and then you have a single replacement reaction that takes place. Now oftentimes circumstances aren't great, a lot of tears are shed, but you have to remember that the provider, if this is a stronger provider, then it can react. If you don't want the reaction to take place, then you're probably going to store your chemicals properly. You want to take precautions. You might not want to get in the car with that other person and go for a ride if you're at work or something like that. People take precautions to prevent themselves from getting into trouble. HBr. You can't split it. It is. You got to put the coefficients up there. 3. Nope, you put 1 because there's 1 there. You see 1, right? Yeah. Yep. Okay, Rain, so we want to balance these polyatomic ions first, these things right here, because they're going to stay together in a group. See how it's OH here? You see how it's OH here? See how it's SO4 here? See how it's SO4 here? So I always try to balance those first, and then I'll come back and check anything else. I won't look at my calciums first. I'll look at these. See how that's the first thing I did? I looked at this, came over here and looked at that. Now I'm seeing the sulfates have 3 there. I'm going to say I'll have 1 there. I can deal with that. It's a 1. So on the test, that's how you'll see it. They'll say, like A will be 3, 1, 3, 2, and B would be like 3, 3, 2, 1. Right? So you're going to say, oh, it's A. Right? Make sense? Yeah, it's just like if you're working in a business. The companies will send you things already packaged, so you have to inventory what you have in the boxes. So that's why this is all the same there. So you got your oxygens balanced. Now just balance the other 2 elements and you're good to go. Which is going to be a 1. Yeah. So when you take a test, it'll be like 2, 1, 1 on the answers. Now be aware when you take your test quiz on Friday, your choices for this are going to be A, 2, 1, 2, or B, 2, 2, 1. right? So you're going to bubble in A as the right choice. That's how they do this. First type of equations we're looking at here are the single replacement reactions, right? And with these reactions, you always have to look at the activity series. So the metal, Lily, we're looking at this. The metal that's more reactive is going to be the one that's going to react with the non-metal group. And what do we mean by more reactive? A better provider. So if you look up here, decreasing reactivity means these are not good providers. Lithium is a better provider. Calcium is a better provider. Sodium is a better provider than these down here. Now calcium is better than sodium. Does everybody see that? And lithium is the best provider on this particular activity series. Any question about that? This is going to provide the electrons with the least amount of resistance. That's why lithium makes good what? Batteries for your phone, right? These always involve an element. Does everybody see there's an element right here? That tells you whatever element is on the periodic table. You see an element and you see a compound, it's single replacement. Now this just happens to be a non-metal. You look at which one's stronger. Is bromine stronger than iodine? Well, you have to look in the periodic table. If you look over here, the one that's closest to fluorine is the strongest. So bromine is stronger than iodine. Fluorine's the strongest, bromine's stronger. So bromine is going to switch with the sodium. Why? Because she's stronger. Just like if you were watching the Olympics last night with the, what were they doing? With the, I forget what that's called. They were snowboarding, but what do they call that? Half pike? I think it was called half pike. Yeah, there was a girl from, I believe, Colorado. I don't follow her enough, but she won the gold. Anybody see that? But she was in competition. Who was her competition? You might know. Yeah, it was China. China was second place, and then just Americans were kind of following that. But it was kind of cool to watch. But the point is that obviously she was a better competitor, so she was able to switch with the sodium, and you form sodium bromide. That's kind of what happened. Here it tells you, what does it tell you? Does it tell you yield or equilibrium? Yeah, it's telling you yield. So what that means is that one of these two is going to be either a solid, liquid, or a gas. It's not going to be aqueous. So once you form a solid, then it's not going to go back to these other things over here. All right. If you put something like, if you have two compounds, you put them in water, and they're both aqueous, that's basically going to be no reaction. Because you're not going to be able to determine if any reaction is taking place. All the ions are just going to be floating around in the water. So you have to have, typically, a solid produced a liquid or a gas over here to know that there's a reaction that takes place. It's the same if you're trying to react to things. You need to know whether they will dissolve in water. So if these won't dissolve in water, they're not going to react. It won't react. So once again, you can have things moving around in equilibrium. You just won't see a reaction unless you have a solid, liquid, or a gas. And if there's no reaction, it's going to be very difficult to separate them because they're all just be mixed around, kind of like salt water. We just call it a mixture. Okay, so when we're examining a double replacement reaction, or just a reaction in general to determine if it's going to take place, we have to look at these solubility rules. And number one up here, it says a substance is considered soluble if more than 3 grams of the substance dissolves in 100 milliliters of water. So, can somebody else read rule number 1 for us on page 974?
All common
Acetates.
Acetates and nitrates are soluble. All binary compounds of group 17 elements other than fluorine. Which metals are soluble except those of silver, mercury, and lead. All sulfates are soluble except those of barium, strontium, lead, calcium, silver, and mercury, except for those in rule 1, carbonates, hydroxates, hydroxides, sulfates, and phosphates are insoluble.
Okay, so combustion reactions always have what as a reactant? O2. What's that? Oxygen? Right. So if you're a firefighter, you want to know if the vehicle's carrying oxygen. Obviously, it's going to be much more flammable because of that. Whether it reacts with oxygen, what you're carrying, there are certain things that are highly reactive to oxygen in the atmosphere. Combustibles. I shut down. Easier once these are balanced because they're not going to break apart. They're typically going to stay together. The one Gabrielle is doing is very difficult to do. I'm very impressed that she got this without any help. So let me explain why it's difficult to do. So this is a trick to help solve these equations. If you start off with just your 6, because you had 6 here, you put 6 there, then your hydrogens are 6, so you put 3 there. You add your oxygens, 3 plus 2, 6 is 12, is 15. You can't take half. You can't put 7.5 there. There's no such thing as a 0.5 O2. These have to be whole numbers. That's the rule. So she had to double everything. So instead of a 6, she put a 12. Instead of a 3, she put a 6. She doubles this. Now it's 15. Doubles that, it's 2. So it's 2, 15, 6, 12. Okay, so double replacement reactions typically involve something called solubility rules. So in the back of the book, there's a reference table to solubility rules. Why are solubility guidelines necessary? Well, without them, we won't know whether the reaction will take place or not. So if you're looking at, let's say, copper 2 hydroxide, it's insoluble. So it's not going to react. There'll be no reaction there. Now, if you do a reaction where you produce a precipitate, which is insoluble, that's what you're typically looking for. Because if both of the reactants and the products are in equilibrium, that means it's going to be difficult to get out of solution what you're looking for. It's dissolved in the water. It's kind of like salt water. If you want, let's say, Epsom salt, try to get Epsom salt out of seawater. It's very difficult to do. So that's one of the problems with mixing things in both the reactants and products are aqueous. Salt water.
You don't need to put the one. I know. One is unnecessary. You just leave it blank.
Yeah, you need the one. Put the one there. Yeah, I'll show you why here in a second. And then one. Good job. Nice job with that. Good job.